So, in this lecture we will look at how to derive the various plane groups based on the two-dimensional lattices we have and the point symmetry operations. So, I have what I have already put down here are the 2D lattices and which are the compatible or consistent point groups that are associated with those lattices. I have a total of 5 2D lattices and 10 2D point groups. So, one thing we can look at that I can add point group 1 to the primitive oblique. So, I will get straight away 2 space groups. I can add M and 2 mm to the primitive rectangular lattice and the centered rectangular lattice, which will give me straight away 4 more plane groups. Then for the primitive square, based on the primitive square, I can add 4 and 4 mm, add them up, I will get 2 more. And then coming to the hexagonal lattice, I can add 3m, 6, 6 mm. So, I will get 4 more plane groups. That gives me a total of 12. But we will see that this is not all. We are going to get even more than 12. But first let us look at these plane groups that we directly get by adding the point groups to the two-dimensional lattices. So, let us start with the oblique lattice. We know that I am going to keep this as my vector A, this out here is the vector B. Oblique lattice can take point group 1 and 2. So, if I add the point group 1, basically there is no symmetry to be shown in the cell, and this is what the plane group would look like. If I were to put an asymmetric motif by using the standard symbol now, then essentially if I put motif here, the translations A and B will take the motif to other 3 locations. So, this only has translation symmetry. Now, with the oblique lattice, I now add the point group 2. Which means that I am going to basically add point symmetry, or rather two-fold rotation symmetry to this oblique cell, and we can add it up at all the lattice points. We can say the lattice points are at the corners. So, I can add up the two-fold rotations at the corner. So, I add it to one corner, translations will take this two-fold to all other corners. But now remember that two-fold with a translation, we go back to the last lecture, two-fold with a translation, there will be another two-fold that will show up in the middle of the translation vector. So, therefore, let me color this differently just to show that this is different. So, I will have a two-fold showing up here. So, which means I will have two-fold on this edge, center edge. I will have two-fold at this center edge also, I will have two-fold at this center edge also, two-fold at this center edge as well. Is there any other place some other symmetry may come up? Well, this is also a lattice translation vector, which means that I will get a two-fold in the center of the diagonal. So, I will get a two-fold here as well. So, by adding this two-fold symmetry, we end up generating many other rotational symmetries around. And if I were to put the motif, let me draw that in a different diagram, otherwise it will get cluttered. So, if I put a asymmetric motif here, 180-degree rotation will generate another motif here. Now, and then now we can simply say the translations will take to all the corners. Now, let us take, we have looked at oblique, let me take before I take rectangular, let me take primitive square. So, primitive square can accommodate 4 and 4 mm. Let me add 4 to this. And we will put the 4-fold at the corners. Now, there are other places also where the 4-fold will come up. A 4-fold and a translation, we saw this in the last lecture, it has to be on the perpendicular bisector of the translation at a distance of t by 2. So, therefore, we will get a 4-fold here, you can get a 4-fold here as well, and this is t by 2. So, if I look at, let us say, this translation on the perpendicular bisector, go up t by 2, it will take me to the center of the cell. Next, anywhere else within the cell, square cell? No, not anywhere else. But now remember that 2-fold is a subset of 4-fold. You look at this, this is my group elements. So, if I pick up these two elements, 1 and a pi, they form a 2-fold, the group 2-fold. So, therefore, there is a 2-fold also operating, a 180-degree rotation, which basically means that I am going to get 2 folds in this case also on the center of the edges of the cell. If I want to put a motif and see how the pattern will evolve, so let me put a motif here, rotation of 90 degrees will bring it here, another rotation of 90 degrees will bring it here, another rotation of 90 degrees will bring it here. And then we can translate all of these 4 . And this is how the pattern would evolve. Now, let us consider now another, this time the hexagonal cell. And let me add a 3-fold. So, remember A in this case would be equal to B, and the angle, basically this angle alpha would be equal to 120 degrees. Add 3 to this. So, hexagonal lattice I am going to add 3. So, I will put it on this figure. I will have a 3-fold at the corners. Now consider this particular threefold. So, again threefold along with the translation, another threefold should show up at some distance on the perpendicular bisector, and that, if we go back, was t by 2 root 3. So, this is t upon 2 root 3. Now, where would this lie? Suppose I take this particular threefold and do a translation of B vector, then where will that threefold evolve? So, we can, what we can do is we can divide this cell into two equilateral triangles, and I have now on the perpendicular bisector, this distance will take me exactly to the centroid of this equilateral triangle, and therefore, a threefold will show up here. Similarly, a threefold will show up here. So, this is the complete symmetry diagram for this particular plane group, and then one can also try to put the motifs on the same diagram. Normally, we will see that those diagrams are made separately, and then these three basically asymmetric objects get transferred through translations. So, I have not drawn exactly the way it should appear, but I hope you get the idea. Now, we also have hexagonal lattice plus point group 6 or the six-fold rotation symmetry. Again, it is the same cell, A equals B and alpha equals 120 degrees. I put a six-fold now. So, I have these hexagonal six-fold rotational symmetries at the corners. Now, I add a translation vector to it first, and let us see what happens. For a 60-degree rotation followed by a translation. For that, we have the result of root 3 by 2 times t. So, this gives me another six-fold out here. So, that was root 3 upon 2 t. So, this is at root 3 upon 2 times t. Now, this is interesting. If I drop a perpendicular out here, this will not look like a perpendicular because I have not drawn a perfect 120 degrees. This actually is the midpoint. So, we start out with this translation, then on the perpendicular bisector, the second hexagonal or six-fold rotational symmetry should appear, and this distance itself is actually root 3 upon 2 times t. Therefore, the second symmetry simply overlaps with the first one. So, no new 6-fold is created. So, now that we have seen this, no new 6-folds get created. So, that is gone, no new 6-fold, but now this 6-fold has a subset of 3-fold as well. So, what would happen? Exactly the same place. So, if I just divide this into 2 equilateral triangles, I will have a 3-fold out here and another 3-fold out here. Now, a 6-fold also has 2-fold as a subgroup, which means that I must get 2 folds as a result of the operation of 180 degrees followed by a translation, and also on the diagonal. So, in this case we ended up with a lot of symmetries, starting with just adding a 6-fold to a hexagonal cell. Now, I am not going to clutter this diagram by drawing more motifs, but you can surely be able to do this. Now, we have covered, so far what we have done is we have looked at basically 1-fold, 2-fold, 3-fold, 4-fold. We have not looked at symmetry, reflection symmetry M yet, and obviously we have not looked at the higher point groups like 2 mm, 4 mm. But now I want to look at what would happen if I add a mirror, and in that case I would use the rectangular lattice, the primitive rectangular and the centered rectangular. So, let us take primitive rectangular and add to this mirror. So, I can add, let us say, a vertical mirror lined up with the edge of the cell. Translation will take this mirror opposite. Also, now remember that sigma followed by a translation vector produces a mirror at the midpoint of the translation. Just go back out here, we can see that we started with 2 mirrors here. For example, if there are 2 mirrors separated by a translation distance, then in between we will get this mirror halfway on the translation. So, therefore, I must get a second mirror located at t by 2, which means I will get a mirror here. So, in fact, that is all the symmetry that would be present in this. So, here we can easily put our motifs to look at the pattern. So, if I put a motif out here, it will reflect by the mirror, it will come here, and then the translations can take it to the other locations.